What's up, team? Quick question before we start. Do you actually know Mosaic AI Vector Search, index types, endpoints, and the storage optimized decision? By the end of this video, you will. Let's dive in. By the end of this video, you'll be able to look at three numbers: vector count, peak queries per second, and latency budget, and pick the right Mosaic AI Vector Search configuration on the spot. We'll walk through index types, embedding modes, the two endpoint shapes, and the one decision that will quietly break your service level agreement if you get it wrong. Quick context before we dive in. DataDino's team has already chunked the fossil corpus into fixed size, overlap-aware records, and written the results into a delta table called fossil chunks, with change data feed turned on. That switch was set deliberately, because today it pays off. Now we need a vector index that can actually serve those chunks at query time, and that means making a configuration call. Before we dive in, let's pin down 5 terms you'll hear throughout this video. A delta sync index auto syncs from a source delta table whenever the rows change. A direct vector access index has no backing table. You push vectors in yourself through the SDK or REST. A standard endpoint is the latency-optimized shape, storing up to around 320 million vectors at dimension 768. A storage-optimized endpoint is the cost-optimized shape that scales past 1 billion vectors, but adds about 250 milliseconds of query latency. And HNSW stands for Hierarchical Navigable Small World. That's the approximate nearest neighbor graph algorithm vector search uses under the hood. Here's the situation on DataDino's desk this week. The fossil corpus has produced 80 million embeddings. The chatbot peaks at 80 queries per second, and the museum's German partner sites have a contractual budget of under 200 milliseconds end-to-end. 3 numbers, 1 configuration call. Pick the wrong endpoint shape, and one of 2 things happens. You blow the latency budget and clients start timing out, or you over-provision and your monthly bill quietly doubles. The choice hinges on 3 numbers a senior engineer holds in their head: vector count, peak queries per second, and latency budget. Those 3 numbers map directly to one endpoint shape, and every other knob you'll touch, index type, embedding mode, sync mode, flows from there. Quick grounding first. Mosaic AI Vector Search is a serverless vector database that sits directly on top of delta tables. It's governed by Unity Catalog, so the same permissions plane that controls who reads your fossil chunks also controls who can query the vector index. It lives next to the lakehouse, not in a separate vendor's cloud, and it's the retrieval substrate behind agents, knowledge assistant, and pretty much every custom retrieval augmented generation application on the platform. The whole configuration space breaks down into 2 axes. Across the top, the endpoint shape, standard or storage optimized. Down the side, the index type, delta sync or direct vector access. Pick one box, and you've defined 90% of how your index behaves. And most of these choices are one-way. So we'll spend the rest of this video learning to pick the right box the first time. Let's start with Delta Sync Index. Think of it as a smart mailbox. You drop a letter into your Delta table, an insert, an update, a delete, and the index automatically pulls that change in. Databricks runs the whole sync pipeline for you. You can create it from the UI, from the SDK, or through the REST API, and it's the default choice when your source of truth already lives in the lakehouse, which for DataDino's fossil chunks table is exactly the case. Direct Vector Access Index is the opposite shape. There's no backing delta table. You hand-deliver every vector yourself, through SDK or REST upserts. You own freshness, you own batching, you own retries. And here's a detail that catches people. You cannot create this index from the UI, SDK or REST only. It's the natural drop-in for teams migrating from Pinecone or Weaviate, because the operational model is the same. Compute vectors client-side, push them in. Side by side, the difference comes down to who owns the pipeline. Delta Sync has a source delta table driving the whole thing, auto-syncs on row changes. You can build it from any of the 3 creation paths, and Databricks runs the extract, transform, load work for you. Pick it when your pipeline already lives in the lakehouse. Direct vector access has no backing table, and it's the right choice when your pipeline lives somewhere else entirely. You own both the embeddings and the freshness story. You push every upsert yourself through the SDK, and there is no UI path, only SDK or REST. Within Delta Sync, you've got a second choice: managed or self-managed embeddings. Managed means you hand Databricks a text column, and it runs a foundation model behind the scenes to embed every row. At query time, you send raw text, and the endpoint embeds your query on its way in. Self-managed means you compute the embeddings yourself and store the vectors in the source table. That's required when your embedding model isn't on the foundation model API, a custom fine-tuned encoder, for instance, or something running on premises. And here's the part that needs to stick. Once you pick self-managed embeddings, you cannot convert that index to a managed one later. There's no migration path, no settings flip, no support ticket workaround. If you decide 6 months in that you'd rather have Databricks handle the embeddings, you're rebuilding the index from scratch. This is an architectural commitment, not a configuration option. The official documentation puts it in one flat sentence: it is not possible to convert a self-managed embedding index to a Databricks managed index. No qualifiers, no path forward. Treat that line the way you'd treat a load-bearing wall. Design around it, don't try to remove it. So the decision rule is straightforward. Default to managed if the foundation model API already has a model that fits your language and dimension needs. Pick self-managed only when you have a concrete, named reason, a custom fine-tuned encoder, an on-premises model, a dimensionality you specifically need. What you absolutely don't want to do is pick self-managed just in case, because the door doesn't swing back. For most English RAG retrieval needs, the Databricks GTE Large English Model covers you at 1024 dimensions, and that's a managed path. Before any index gets created, the first 2 switches always need to be on. First, Unity Catalog. The workspace has to be UC enabled, there's no Hive Metastore path here. Second, Serverless compute needs to be turned on in the workspace. The third switch is conditional. Change data feed has to be enabled on the source delta table for a Delta Sync index on a standard endpoint, because that endpoint relies on incremental change tracking to keep the index fresh. On a storage-optimized endpoint, change data feed is not required, because every triggered sync partially rebuilds the index instead of consuming incremental changes. Miss any required switch, and index creation fails with no helpful nudge. You just get an error. If you're going to remember one failure mode, make it this one. Change data feed not enabled on the source delta table is the single most common reason a Delta Sync index on a standard endpoint either fails to create or silently never refreshes. If you're on a storage-optimized endpoint, this one does not apply. Change data feed is not required there. DataDino's fossil chunks table has it on anyway, because the team set the delta.enable change data feed table property when preparing the source table. That one property is what makes today's standard endpoint work possible. Let's pause and consolidate. 2 index types: Delta Sync that auto-syncs from a table, and direct vector access where you push via SDK2 embedding modes, managed where Databricks embeds for you, and self-managed where you embed yourself, with that one-way door between them. For Delta Sync on a standard endpoint, you need 3 prerequisites: Unity Catalog, Serverless compute, and change data feed on the source table. On a storage-optimized endpoint, only the first 2 apply. With the index side settled, the next question is what kind of endpoint hosts it. The standard endpoint is the sports car. It's designed for latency-critical workloads, with typical query latencies in the single-digit to tens of milliseconds range, depending on index size and dimensionality. The contrast worth holding in your head is that storage optimized starts at a floor of around 250 milliseconds. Capacity sits at roughly 320 million vectors at dimension 768. That's the first of the three numbers we want you to memorize. It supports both continuous sync and triggered sync, so you have flexibility on freshness. Pick this when a service level agreement is forcing your end-to-end response under a few hundred milliseconds. The general guidance from Databricks is: choose standard endpoints when latency is critical and your index is well under 320 million vectors. That's the rule. In one sentence, two conditions: latency matters, and you're comfortably under the ceiling. Both have to be true. Storage optimized is the freight train. It scales to over 1 billion vectors at dimension 768. That's the second number to memorize. The embedding dimension has to be divisible by 16, which constrains your model choice. It supports triggered sync only. There's no continuous mode here, and it adds about 250 milliseconds of query latency per call, in exchange for being up to 7 times cheaper per vector. That's the trade-off in one sentence. Here it is from the docs. Storage-optimized endpoints accommodate over 1 billion vectors at dimension 768, with 10 to 20 times faster indexing, but incur approximately 250 milliseconds additional query latency. Notice what that quote does. It stacks the headline capability, the ingest speedup, and the latency cost all in one breath. That's the shape of the deal. There's a list of things storage optimized just can't do today, and these are the constraints that force the decision. No continuous sync, triggered only. No FedRAMP coverage, which is a hard blocker for federal workloads. No customer-managed keys, which rules out a lot of regulated industries, and the embedding dimension constraint, divisible by 16, is a real consideration if you're bringing your own model. Standard versus storage optimized, side by side. Standard handles roughly 320 million vectors at dimension 768, queries in single-digit to tens of milliseconds depending on index size and dimensionality, supports both sync modes, has FedRAMP and customer-managed keys, and is built for latency-critical work. Storage-optimized handles over 1 billion vectors at the same dimension, adds 250 milliseconds as a latency floor, supports triggered sync only, has no FedRAMP and no customer-managed keys, but is up to 7 times cheaper per vector. The rest of the decision is just matching your workload to the right column. Visually, the capacity gap looks like this. Standard tops out at around 320 million vectors at dimension 768. Storage optimized stretches past 1 billion at the same dimension. That's roughly 3 times the headroom for the same vector size. If you're planning a petabyte scale corpus, standard simply can't hold it. And here's the other side of the deal. Standard endpoints serve queries with low latency, single-digit to tens of milliseconds, depending on index size and dimensionality. Storage optimized adds about 250 milliseconds on top, and that's a floor, not an average. For a service-level agreement under 200 milliseconds end-to-end, storage optimized is mathematically impossible. The latency floor alone exceeds your entire budget. And this is why engineers pick storage optimized when they can. At billion vector scale, Databricks reports cost efficiencies of up to about 7 times cheaper per vector compared to prior architectures. That kind of multiplier, applied month after month to the same retrieval workload, is what pays for the latency trade-off at scale. Quick word on the 2 sync modes. Continuous sync runs a streaming pipeline on a provisioned compute cluster that's kept warm, giving you seconds of freshness. It's standard endpoints only. It's the highest cost option because the compute is always parked, and you pick it for workflows where someone edits a document and queries against the change moments later. Triggered sync pulls on demand from the Delta table. It's cheaper because no streaming compute is idling. It works on both endpoint types, and crucially, it's the only mode storage optimized supports. Pick triggered for batch refresh cadences, nightly, hourly, whatever fits your data. 2/3 of the way through. Standard is the sports car, around 320 million vectors, 20 to 50 millisecond queries, both sync modes available. Storage optimized is the freight train, over 1 billion vectors, plus 250 milliseconds per query, triggered sync only. At petabyte scale, the cost difference reaches roughly 7 times. Now let's compress all of that into the rule a senior engineer actually uses at the whiteboard. These are the 3 numbers to memorize. 320 million is the standard endpoint ceiling. 1 billion is the storage optimized capacity. Dimension 768 is the baseline both of those numbers are quoted against. If you can hold those 3 in your head, you can walk into any vector search architecture conversation and immediately frame the decision. Here's the actual flow. Start with vector count. How many embeddings will the index hold at peak? Then check the latency budget. What's the end-to-end ceiling? Then check peak queries per second. How much traffic at the busiest hour? Those 3 inputs collapse to one of 2 outcomes. Under 320 million vectors and latency critical pushes you towards standard. 10 million or more vectors with room in the latency budget for that 250 millisecond floor pushes you towards storage optimized. Here's the general guidance from Databricks on when to choose storage optimized. Pick it when you're working with 10 million or more vectors, can tolerate some extra latency, and need better cost efficiency per vector, up to 7 times cheaper. 3 conditions, all 3 must hold. If even one of them fails, especially the latency tolerance, standard is your answer. Let's run DataDino through the rule. 80 million embeddings sit comfortably under the 320 million standard ceiling, plenty of headroom for growth. The sub-200 millisecond budget cannot absorb the 250 millisecond storage optimized floor. That's the disqualifier. 80 queries per second sits right at the boundary where capacity planning starts to matter, and we'll come back to that in a moment. The verdict: standard endpoint, delta sync from the fossil chunks table, with hybrid search layered on top. Hybrid search, by the way, just means combining vector similarity with traditional keyword matching to catch results either approach alone would miss. Standard endpoint is the call. Could storage optimized save DataDino money on infrastructure? Yes, meaningfully. Would it also break the service level agreement on every German query? Also yes. Saving money on a system that doesn't meet its contract isn't saving money. It's building the wrong thing cheaper. One realism note on throughput before we move on. A single endpoint's approximate nearest neighbor throughput plateaus around 30 queries per second. Once the index outgrows 1 vector search unit, that's an approximate figure from Databricks guidance. DataDino's 80 queries per second peak needs either the high QPS feature or sharding across multiple endpoints. As an approximate lever, halving your embedding dimensionality typically improves throughput by around 1.5 times and cuts latency by around 20%, and re-ranking sits on top of all this as a separate optimization layer. So how does vector search return results in tens of milliseconds when there are hundreds of millions of vectors to search? The algorithm is HNSW, Hierarchical Navigable Small World, an approximate nearest neighbor graph. Picture a city with express buses connecting distant hubs and local buses connecting nearby stops. You ride the express buses to get close, then switch to local buses to walk in the last few blocks. The trade-off: results are approximate, not exact. You may miss the absolute best match occasionally, but you save enormous amounts of compute compared to a brute force search over all vectors. And here's the metric detail that surprises almost everyone. The default distance metric is L2, Euclidean distance, not cosine similarity. If you want cosine behavior, You have to normalize your embeddings at index time and at query time. Skip either side, and the math falls apart. The good news, on unit length vectors, L2 and cosine produce the same ranking order. According to the Databricks AI Search documentation, AI Search uses the HNSW algorithm for its approximate nearest neighbor searches, and the L2 distance metric is the default. If you want to use cosine similarity, you need to normalize your data point embeddings before feeding them into the vector search algorithm. That single rule covers the algorithm, the metric, and the workaround all at once. Here's the bug that bites teams on both paths, and the part most people get wrong. Neither the managed path nor the direct vector access path guarantees normalized embeddings for you. In particular, the default managed model, GTE Large English, explicitly does not produce normalized vectors, so the L2 default does not silently become cosine just because you picked the managed option. If you skip normalization, your similarity scores can be numerically very different from cosine values you compute locally, potentially orders of magnitude off depending on your embedding magnitudes. The rule is simple. If you need cosine equivalent rankings, normalize embeddings explicitly on both the index side and the query side, regardless of which embedding mode you chose. Here's what creating DataDino's index actually looks like in code. The notable pattern is what's not there. We point at the source table, fossil chunks. We name the index. We pick triggered sync. We hand over a text column and the name of a managed embedding endpoint, the Databricks GTE Large English Model, a foundation model embedding endpoint for English text. Notice we never compute a single embedding ourselves. That's the managed delta sync path in 9 lines. Here are the 5 mistakes most teams make, paired with their fixes. Forgot change data feed on the source table. Fix is to set the enable change data feed delta table property to true. Picked self-managed embeddings just in case. Default to managed unless you have a real, named reason. Picked storage optimized for a sub 200 millisecond service level agreement. Standard endpoint is the only valid choice when latency is critical. Use direct vector access without normalizing. Normalize at index time and at query time, and tried to create a direct vector access index from the UI. Use the SDK or REST, because the UI doesn't support it. Pulling it all together, 3 numbers in your head, 320 million, 1 billion, dimension 768, 2 endpoint shapes, standard for latency, storage optimized for scale and cost, 2 index types, delta sync that auto-pulls from a table, and direct vector access where you push via SDK one-way doors. Self-managed embeddings cannot convert to managed later. And for prerequisites, Unity Catalog and serverless compute are always required, and change data feed is required for delta sync on standard endpoints, but not on storage optimized. Now let's see how well that landed with a quick 5-question quiz. Alright, let's test what you've learned. Question 1. A team is building a RAG application with 90 million embeddings, a peak load of 60 queries per second, and an end-to-end latency budget of 180 milliseconds. Which endpoint configuration is the correct choice? Is it A, storage optimized endpoint, because the cost savings justify the latency trade-off? B, standard endpoint, because the latency budget cannot absorb storage optimized's 250 millisecond floor? C, storage optimized endpoint, because 90 million vectors exceeds standard's capacity? Or D, either endpoint works equally well at this scale? Take a moment to think about it. The answer is B. Storage optimized adds about 250 milliseconds of query latency, and that floor alone blows past the 180 millisecond budget. 90 million vectors sits well under the 320 million standard ceiling, so standard is both feasible and required. Question 2. An engineer creates a direct vector access index and computes embeddings using a fine-tuned model locally. Similarity scores returned by vector search are about 270 times different from manual cosine similarity calculations against the same vectors. What is the most likely cause? Is it A, the endpoint is using the wrong embedding model internally? B, change data feed is not enabled on the source table? C, the embeddings were not L2 normalized before upserting? Vector search uses L2 distance by default, not cosine. Or D, the index was created with a storage-optimized endpoint that does not support cosine similarity. Take a moment to think about it. The answer is C. Vector search defaults to L2 distance, not cosine, and neither the managed path nor direct vector access normalizes embeddings for you. The default model does not produce normalized vectors. You have to normalize client-side before upserting and at query time. Skip it, and the score numbers will be wildly off from anything you compute locally. Question 3. A team launched a Delta Sync index with self-managed embeddings 6 months ago. They now want to switch to Databricks managed embeddings to reduce operational overhead. What is the supported path? Is it A, update the index configuration to set embedding mode to managed and trigger a resync? B, run a one-time conversion job through the Vector Search SDK? C, open a Databricks support ticket to request a migration? Or D, create a new index with managed embeddings and rebuild from the source table? Conversion is not supported. Take a moment to think about it. The answer is D. The documentation is explicit. It is not possible to convert a self-managed embedding index to a Databricks managed index. There's no settings flip, no conversion job, no support workaround. The only path forward is rebuilding from scratch. Question 4. A federal agency needs to deploy ARAG system over 800 million internal documents. Requirements include FedRAMP compliance, customer-managed encryption keys, and tolerance for queries up to 400 milliseconds. Which endpoint should they choose? Is it A, storage optimized, because 800 million vectors exceeds standard's 320 million ceiling? B, standard, because storage optimized does not support FedRAMP or customer-managed keys? C, storage optimized, because the latency budget can absorb the 250 millisecond floor? Or D, either endpoint, sharding traffic across both for cost optimization? Take a moment to think about it. The answer is B. Storage optimized does not currently support FedRAMP or customer-managed keys, and those are non-negotiable compliance requirements, so standard is the only compliant choice. But 800 million vectors exceeds a single standard endpoint's 320 million ceiling, which means the team has to shard the workload across multiple standard endpoints. That adds architectural complexity, but it's the price of meeting both the compliance and the capacity constraints at the same time. Question 5. Let's test a concept related to preparing tables for vector search. After provisioning a standard endpoint, a team notices that updates to the source Delta table never appear in their Delta Sync index. No errors are raised, but newly inserted rows are missing from query results. What is the most likely cause? Is it A, the endpoint is undersized and is silently dropping sync events? B, self-managed embeddings were chosen but no vectors were pre-computed for the new rows? C, change data feed was never enabled on the source Delta table? Or D, the pipeline type was set to triggered instead of continuous? Take a moment to think about it. The answer is C. For Delta Sync indexes on standard endpoints, change data feed has to be enabled on the source Delta table, so the index can detect and apply incremental row changes. Without it, the index either fails to create or silently never refreshes after the initial load, and silent never refreshes is exactly the symptom described. The fix is to set the enable change data feed delta table property to true on the source table before creating the index. One important qualifier: storage optimized endpoints do not need change data feed because they perform a partial rebuild on each triggered sync. But on a standard endpoint, like the one in this scenario, this is the single most common configuration failure. That wraps up Mosaic AI Vector Search, index types, endpoints, and the storage-optimized decision. The Databricks GenAI Engineer cert has more videos coming on the trickier topics. Subscribe so the algorithm tells you when. Thanks for watching.